Welcome to Science for Sleepy, the little corner of the universe where you can settle in under the covers. Close your eyes if you wish, and let science guide you gently into both wonder and rest. Tonight's story is a big one, and when I say big, I mean bigger than anything you have ever thought about. We are going to talk about what will happen when our home galaxy, the Milky Way, collides with our giant neighbor, the Andromeda Galaxy. The event is so vast that your mind might resist believing it is real. Yet it is real, as certain as tomorrow's sunrise, except tomorrow in this case is billions of years away. Let's begin with a few shocking facts to wake up your imagination. The Milky Way, which holds our sun and Earth, is not standing still in space. It is speeding along at hundreds of thousands of miles every single hour, tugged by the gravity of nearby galaxies. At the same time, the Andromeda Galaxy, which is even bigger than ours, is hurtling directly toward us. These two giants are on a cosmic collision course. And here's the part that makes people pause. The collision has already begun, in the sense that the invisible arms of gravity are pulling the galaxies together right now. Imagine two giant clouds of fireflies passing through one another in slow motion. That is closer to the truth than thinking about car crashes or even planet crashes. Now, before we drift too far into the details, can I ask you a little favor? If you could, take a moment to scroll down into the comments and let us know where you are listening from and what time it is right now where you are. And while you're down there, consider subscribing to Science for Sleepy. We upload every single day, so if you come back tomorrow, there will be another story waiting for you. Now let's drift back to the immensity of what is unfolding in space. To picture the collision, you must first understand just how enormous these galaxies are. The Milky Way alone contains hundreds of billions of stars, and countless planets orbiting around them. Some of those planets may have their own forms of life quietly staring into their night skies, completely unaware that their galaxy, too, is heading toward a slow embrace with another. The Andromeda Galaxy is even larger, with its great spiral arms stretched wide across 200,000 light-years. And here we are, tiny humans on a small planet, speaking about it like we are outside observers. In truth, we are not outside of it. We are inside this story, passengers in one of the smaller cars of the cosmic train. When you think about it, there is something both terrifying and comforting in this. Terrifying because the scale makes you realize how small you are. Comforting because the collision will not happen tomorrow or even within the lifetime of our species. It is predicted to occur in about 4 billion years. That means that by the time the first sparks of contact take place, Earth itself may be a very different world, perhaps unrecognizable from what it is now. The continents may have drifted into new shapes, new species may have risen and fallen, or perhaps humanity itself will have evolved into something else entirely if we still exist at all. But despite how far away it feels, the scientists who study this collision treat it not like science fiction, but like science fact. They have gathered their evidence through slow, patient, and almost boring measurements. Using telescopes, they studied the light from Andromeda and noticed something surprising. The light is not red-shifted, as it would be if Andromeda were moving away from us, but blue-shifted. That means it is moving toward us, its light waves compressed as it approaches. The exact speed has been measured again and again, confirming the truth. Andromeda is on its way here, at a breathtaking pace of hundreds of kilometers every second. Pause for a moment, and try to imagine what it means for something as massive as an entire galaxy to move at such speed. Our minds are used to thinking about cars, planes, or maybe rockets. A rocket leaving Earth feels unimaginably fast, but compared to a galaxy, it is nothing more than a feather drifting in the breeze. These galaxies, each containing stars, black holes, gas clouds, and dust, are like cosmic cruise ships barreling across the ocean of the universe. This is where the detail becomes both dull and fascinating. When the Milky Way and Andromeda collide, it will not be an explosion, but a process drawn out over billions of years. At first, the edges of the galaxies will stretch and distort, pulled by each other's gravity. Stars will be flung into new orbits, some cast out into the void, others drawn closer together. The great spiral arms will tangle, like strands of two giant spiderwebs meeting in the dark. Slowly, over a long time, the two galaxies will merge into one larger, more rounded galaxy. Astronomers even have a name for this future creation, Milkdromeda, a word that sounds almost silly but hides a very serious reality. What is striking is how calm the process will seem if you were to watch it in real time. If you had a window that let you see the collision as it unfolds, you would not notice anything within a human lifetime. To you, the stars would appear fixed, unmoving, but across millions of years, the slow ballet would reveal itself. This is one of those truths about space that can feel boring at first glance, because nothing seems to happen quickly. But that slowness is the point. The universe does not rush. The universe moves on a scale beyond our impatience. This leads us to a strange reflection. If the universe is so patient, then what does that say about us? We are creatures of short lives, rushing through minutes, hours, and days, trying to fit meaning into them. Meanwhile, the galaxies carry on with their business over spans of time so long that they stretch beyond our imagination. Perhaps the greatest lesson here is not about the collision itself, but about perspective. The collision will come, but not for billions of years. That fact alone changes nothing in our daily lives, yet it reveals something profound about the place we occupy in the cosmos. The thought you may now be holding in your mind is whether this event matters to us at all. After all, why think about a collision that we will never see? Perhaps because in doing so, you connect with the story of the universe, a story you are already a part of. Just as a person might study family history to know where they came from, we study cosmic history to know where our galaxy is going. And in a strange, quiet way, that knowledge matters. But here is a question to leave lingering as you settle further into your bed tonight. If the Milky Way and Andromeda are destined to merge into one, what else in the universe is slowly and invisibly moving towards something it cannot avoid? If you are still with me, still tucked in, listening to the quiet drift of this story, then let's slow things down and peel back one of the simplest but most overlooked questions. What is a galaxy really? Before we imagine them colliding, we have to understand what these vast structures actually are. And I want you to stay with me here, even if the details feel a little dry at first, because those very details are the glue that holds this whole cosmic picture together. A galaxy is not just a cluster of stars. Those stars are the parts we notice most because they shine. A galaxy is an ecosystem, built of different ingredients layered and woven together over billions of years. First, there are the stars themselves, hundreds of billions in each galaxy. They are not evenly spread out, but gathered into shapes, spirals, and halos. Then there are planets, moons, and asteroids orbiting those stars, silent companions that make up the majority of solid matter. Beyond that are the great clouds of gas, hydrogen, and helium, mostly that drift like invisible oceans, waiting to collapse under gravity and give birth to new stars. Then comes dust, tiny grains scattered through the galaxy, so fine you would not see them if they floated through your living room. But in space, dust reshapes the light of distant suns. And then there is the part that is both boring and haunting, dark matter. You cannot see it, cannot touch it, cannot measure it directly. But without it, the galaxy would not hold together. It acts like a hidden skeleton, an invisible framework that keeps everything spinning in place. If you only counted the stars and gas, the galaxies would not have enough gravity to prevent themselves from flying apart. So, astronomers realized there must be something else, something unseen, making up more than 80% of all the matter in the universe. They called it dark matter, and although it is an invisible player in our story, it is perhaps the most important of all. Now imagine each galaxy, Milky Way, and Andromeda alike as a floating city in the night. But unlike cities we know, galaxies are not built in days or years. They are the product of more than 13 billion years of cosmic history. To understand them is to trace back the slow layering of events that shaped them: small galaxies merging into larger ones, gas collapsing into stars, stars exploding into supernovae and spreading heavy elements like iron, carbon, and gold which later formed planets and, in our case, life. You might wonder why we bother to learn all of this. And here is where history comes in. Long before we knew the word galaxy, people looked up at the sky and saw a hazy band of light. They called it the Milky Way, naming it after milk spilled across the heavens. To them, it was not a galaxy at all, but part of the sky itself. It wasn't until the early 20th century that astronomers, using larger telescopes, realized that some of those fuzzy smudges of light we call nebulae were not inside the Milky Way at all. They were entire galaxies, millions of light years away. That realization was one of the great shifts in human understanding. Overnight, the universe became vastly larger than anyone had imagined. So when we talk about the collision of galaxies today, we are not simply telling a bedtime story. We are continuing that tradition of expanding the human perspective. Just as our ancestors widened their view from Earth to the solar system, and from the solar system to the galaxy, we are now widening it further, seeing galaxies not as fixed and separate, but as actors in a slow and endless dance. But let's return to the details, because it is the details that give weight to this picture. A galaxy like the Milky Way is a disk, a flat spiral stretching about 100,000 light-years across. At its center lies a bulge of older stars, and deep in the very core, a supermassive black hole called Sagittarius A star. Around this disk is a halo, a faint sphere of stars and clusters that extends far beyond the main spiral arms. Andromeda is similar but larger, about 200,000 light-years across, with its own central black hole. These two systems are not floating alone. They are part of a larger family of galaxies, the Local Group, which includes dozens of smaller galaxies like the Magellanic Clouds. The Local Group itself is drifting through space, part of an even greater web of galaxies stretching across the universe. If you are lying in bed, listening to this, maybe your eyelids feel heavy now, but let me ask you to picture something slowly. Imagine zooming out from Earth, leaving your room, your city, your continent, floating beyond the clouds, past the moon, beyond the solar system, until you see the Milky Way in all its vastness. Now, shift your gaze and imagine the Andromeda Galaxy approaching across empty space, a grand spiral that looks faint but steady. These are not abstract ideas. They are real, and they are moving toward one another, carrying their stars, their gas, their black holes, and yes, their dark matter skeletons with them. What is fascinating is that this picture, as immense as it is made possible by boring details, the measuring of light, the mapping of stars, the careful cataloguing of galaxies. Without the slow, patient work of countless astronomers, we would not even know the collision was coming. And here lies another strange lesson. Sometimes the most exciting truths are discovered through the dullest steps. Science, in that way, mirrors the galaxies themselves. From small, slow actions, something vast is built. Now, let's make this personal for just a moment. If you have ever walked into a crowded street fair, you might have noticed how people weave around one another without actually bumping into each other most of the time. Galaxies are like that, except stretched across unimaginable scales. They are crowds of stars moving together, yet separated by such vast distances that even in a collision, they mostly slip past one another. In fact, if you think of our own sun, the nearest star to it is over 4 light-years away. That's trillions of miles. So when two galaxies merge, it is almost as if two swarms of bees flew through each other, with each bee rarely touching another. The drama is not in the collisions of individual stars, but in the reshaping of the whole swarm. Yet even knowing all of this, there is something poetic about the word collision. We imagine violence, destruction, drama, but the truth is gentler, slower, more patient. The galaxies do not shatter. They stretch, they bend, they pull. They remake themselves, and in doing so, they create new stars, new patterns, new histories. And here is something you might not have thought about before. When we speak of galaxies, we speak of them as if they were objects, like stones or buildings. But really, they are processes. A galaxy is not a thing so much as a living history of motion, change, and transformation. So when Andromeda and the Milky Way meet, we should not think of it as two objects colliding, but as two processes intertwining. This leads to a thought I want to leave you with at the end of this section. If galaxies are processes, and if even something so immense and seemingly permanent is actually in motion, then what does that mean for the way we think about permanence in our own small lives? So far, we have set the stage by looking at the enormity of galaxies and what they are made of. Now let's shift into the story of how scientists even figured out that this collision was coming. Because at first glance, you would never know. When you step outside on a clear night, the stars seem fixed in the sky. The constellations look the same as they did for the ancient Greeks, or for the people who lived thousands of years before them. To the human eye, everything appears motionless. So how did astronomers, those patient watchers of the sky, manage to discover that something as large as the Andromeda Galaxy is actually barreling toward us? The answer lies in the very slow, very boring art of measurement. Imagine standing by a road and watching a car far in the distance. At first, you may not notice it moving toward you, but if you keep your eyes on it long enough, or if you use a tool to measure the sound of its engine, you begin to notice it growing closer. Astronomers face a similar challenge. They cannot watch a galaxy move over a human lifetime because the distances are far too great, so instead, they rely on the light the galaxy gives off. This is where the Doppler effect comes in, something you may have experienced without even realizing it. Think about how an ambulance siren sounds different when it rushes toward you compared to when it moves away. As it approaches, the sound waves are compressed, and the pitch rises. As it moves away, the waves stretch, and the pitch falls. Light behaves in a similar way. When an object in space is moving away from us, the light waves stretch, and the light shifts toward the red end of the spectrum. When it is moving toward us, the light waves compress, and the color shifts toward blue. When astronomers pointed their telescopes at the Andromeda Galaxy and measured its light, they found something shocking. The light was blue shifted. That meant Andromeda was not drifting away from us, as one might expect in an expanding universe, but directly approaching. And not at a lazy pace either. It is speeding toward the Milky Way at over 100 kilometers every second. Imagine that for a moment. Every single second. It closes the gap between us by more than 100 kilometers. That is faster than anything we could ever build on Earth. Faster than rockets, faster than jets, faster even than the imagination of early astronomers who first measured it. And here's the curious part. When these measurements were first made, not everyone accepted them. Science is slow to change its mind, and for good reason. Extraordinary claims require extraordinary evidence. The astronomers had to refine their tools, measure again and again and again, until finally the evidence became undeniable. Andromeda is not just sitting still in the sky, it is on a path toward us, and gravity is in control. Now, think about the patience involved here. These were not discoveries made overnight. They were the result of decades of work, refining instruments, polishing mirrors, recording data. Some of the earliest hints came from the painstaking work of measuring star positions on glass photographic plates. It sounds almost quaint today, like something from an era of dusty observatories and candlelit journals. Yet, it was in those dusty details that the grand story of a galactic collision was revealed. And the story grows deeper when you consider how this ties into our understanding of the universe's expansion. In the 1920s, Edwin Hubble made the groundbreaking discovery that galaxies are moving away from us, and the universe itself is expanding. That means most galaxies show a red shift in their light, but Andromeda stands out as one of the rare exceptions. Instead of receding, it is approaching. This unusual case is what makes it so important, because it shows that while the universe expands overall, local groups of galaxies are bound together by gravity, pulled into each other's arms despite the wider expansion. There is something poetic in this contradiction. On the grand scale, everything is flying apart. Yet on the smaller scale of galaxy groups, things are drawn together. It is as if the universe is both a scattering and a gathering, a push and a pull all at once. For you, lying in bed and listening, perhaps the idea of astronomers carefully measuring wavelengths of light sounds a little dull, and it is. But in that dullness lies something deeply meaningful. Every small observation, every precise calculation, was a brick in the foundation of knowledge. It is because of those details that we can now say with confidence, our galaxy has a date with Andromeda, and the meeting is written into the fabric of gravity itself. There is also a human story here. Many of the astronomers who worked on these measurements would never live to see the public excitement about Andromeda's collision. They devoted their lives to data, perhaps not knowing that decades later, their work would feed into bedtime stories like this one. There is a humility in that kind of science, the willingness to spend one's life on something that may not seem dramatic in the moment, but that adds up to something astonishing in the long arc of time. This makes me wonder how many other truths about the universe are sitting quietly in data we have already collected, waiting for someone to connect the dots. How many ideas that feel fixed and eternal today will look different when the patient eyes of tomorrow's scientists re-examine them? And here is the question to leave you with as you rest tonight. If the collision of two galaxies can be discovered through something as small and invisible as the shift in starlight, what other massive truths might be hidden in the tiny details we overlook every day? When we speak about the future collision of the Milky Way and Andromeda, one of the most difficult parts to grasp is the time scale. Astronomers tell us this event will begin in about 4 billion years. 4 billion, the number alone slides past the human mind, because we are used to thinking in days, years, maybe centuries. What does 4 billion years even mean to a creature who rarely lives beyond 100? Let's try to untangle this. If you think about your own life, maybe it feels long when you measure it in school years or in decades. A century feels almost infinite, but if you line up centuries, you only need 40 of them to cover the span of recorded human history. That's just 4,000 years. And in that time, empires have risen and fallen, languages have been born and died, and every single person you have ever read about in a history book has lived and passed away. Yet 4,000 years is not even a speck compared to 4 billion. Let's zoom out further. The dinosaurs roamed the Earth about 65 million years ago. To us, that feels unimaginably distant. And yet 65 million is still tiny compared to 4 billion. If you stacked 65 million on top of itself again and again, you would need to do it more than 60 times to equal the time until Andromeda and the Milky Way meet. Even the age of Earth itself, about 4.5 billion years, is only slightly longer than the time we are waiting for this cosmic encounter. In other words, the galaxy collision is not just some far-off dream. It is set to happen on a timescale comparable to the entire lifespan of our planet. This is where the detail becomes quietly humbling. While we live our days in 24-hour cycles and our years in 365-day rotations around the sun, the universe ticks along on a clock so large that even continents, oceans, and species come and go in what feels like moments. Imagine if you could sit in a chair outside of time, watching Earth and its history unfold at high speed. Civilizations would rise and fall like flickering lights. Ice ages would come and go like breaths. And across it all, galaxies would drift slowly toward each other, patient and unhurried. Now, why does this matter? You might think if the event is so far away, why even bother speaking about it? The answer lies in the way human beings use imagination. Even though we will not be here in 4 billion years, picturing that timescale stretches our thinking. It forces us to see our lives differently, to realize how brief we are, but also how remarkable it is that we can even conceive of something so vast. There is also a practical side. Understanding timescales helps scientists place events in context. If we know when galaxies will collide, we can also think about what the Sun will be doing at that time. In about 5 billion years, our Sun is expected to expand into a red giant, swallowing Mercury and Venus, and perhaps Earth as well. So the galaxy collision and the Sun's transformation will overlap in cosmic time. Two great events, unfolding together, neither of which humanity as we know it will witness. but both of which shape the destiny of our cosmic neighborhood. Sometimes, when people hear this, they feel a little sad or even frightened. The idea that Earth and our Sun are temporary can sound like a loss. But there is another way to think of it. Just as each human life is brief but meaningful, so too is the life of a star or even a galaxy. Impermanence is not a flaw of the universe. It is its very nature. Things exist, change, transform, and make way for new things. In this way, the collision of galaxies billions of years from now is not a tragedy. It is a continuation of a process that has always been happening. Let's bring this back down to a scale you can picture. Imagine a calendar year, from January to December. If you compress the entire history of Earth into that single year, humans as a species would only appear in the last few minutes of December 31st. Civilization as we know it would fit into the last seconds before midnight. And yet, in that same calendar, the Milky Way and Andromeda collision would not happen until many, many future years on the calendar. We live not even at the end of the year, but in a blink of a moment, while the greater story continues long after. There is another angle here that makes the waiting time meaningful. 4 billion years may be beyond human imagination, but to astronomers, it is precise enough that they can create models and predictions. Supercomputers run simulations of how stars will move, how galaxies will twist, how gravity will reshape everything. These simulations are like time machines, letting us peek into the far future, even if we cannot live it ourselves. And so, in a way, we do witness it not by waiting billions of years, but by turning equations into visions, numbers into images. If you've ever watched one of those computer animations of the Milky Way and Andromeda colliding, you may have noticed how graceful they look, like two dancers moving closer, swirling around each other, before finally merging into one. Those animations condense billions of years into a few seconds, letting us see in a blink what would otherwise unfold too slowly for us to perceive. And this, too, is a reminder about time. Sometimes we need to compress or stretch time in our minds to grasp truths we cannot otherwise hold. And here is something to think about as you rest tonight. If we know that galaxies move toward one another over billions of years, then what else in our own short lives might be moving slowly, too slowly for us to notice? What patterns, what changes, what destinies are unfolding around us right now, invisible only because our lives are too brief to measure them? When you hear that two galaxies are on a collision course, the natural question is, why? Why should two such enormous structures, separated by millions of light years, move toward each other instead of drifting peacefully apart forever? The answer is both simple and mysterious, resting in the quiet but relentless power of gravity. Gravity is one of those forces you live with every single day, so familiar that you rarely think about it. You drop a pen and it falls to the floor. You jump and you come back down. You set a glass on a table and it stays put. These everyday examples make gravity seem ordinary, almost boring. But gravity is also the architect of the cosmos. Without it, stars would not form, planets would not orbit, and galaxies would not exist. And when it comes to the Milky Way and Andromeda, gravity is the thread that is pulling them together, slowly but without pause. Let's strip this down to its basics. Every object with mass exerts a pull on every other object. That means you are pulling on the Earth right now, just as the Earth pulls on you. Of course, your mass is so small compared to the Earth that your pull doesn't make much difference. But scale that idea up. A galaxy, with its hundreds of billions of stars, has an enormous amount of mass. Two galaxies close enough to one another will not drift apart. They will fall together, bound by their mutual attraction. And that is exactly what is happening with our galaxy and Andromeda. Now, the interesting part is that this pull of gravity competes with another great force, the expansion of the universe. On the largest scales, galaxies are carried away from each other as space itself expands. That's why most galaxies are redshifted, receding from us. But in smaller neighborhoods of the universe, gravity can overcome that expansion. Imagine baking a loaf of raisin bread. As the dough rises in the oven, The raisins all move apart. That's like the expansion of space. But if two raisins are close enough, the stickiness of the dough might keep them together. The local group, the cluster of galaxies we live in, is like those raisins bound together despite the wider expansion. So why does this matter? Because it shows that the collision of the Milky Way and Andromeda is not just a random accident. It is the inevitable outcome of laws that are woven into the fabric of reality. And once those laws are in motion, there is no stopping them. Galaxies cannot choose to avoid one another. They are bound to follow the paths gravity has written for them. Think for a moment about the patience of this force. Gravity does not hurry. It works slowly, invisibly, over immense distances and unimaginable timescales. It is not dramatic, like an explosion or a storm. It is quiet, persistent, always pulling, never resting. And yet it shapes everything. In your life, you may think of dramatic events as the ones that change the course of history. But in the universe, the great shaper is this steady, dull, but unstoppable force that simply pulls and pulls until the inevitable happens. There is also something curious about how gravity works when you scale it up to galaxies. Inside a galaxy, stars orbit around the center, like bees circling a hive. They do so because of gravity, not just from the visible stars, but from the dark matter halo surrounding the galaxy. When two galaxies approach, these halos are the first to feel each other's tug. Long before the visible stars start to mingle, the invisible skeletons of dark matter are already entwining. It is as though the galaxies are shaking hands in the dark, long before their luminous faces touch. If you could watch this process unfold in slow motion, you might imagine the galaxies as two ships at sea, slowly drawn together not by engines or sails, but by the invisible current of the ocean beneath them. No matter how they try to drift apart, the water always brings them closer. In the case of Andromeda and the Milky Way, the current is gravity, and the ocean is the very fabric of space-time. Another important detail is that this gravitational pull doesn't just bring galaxies together. It also reshapes them as they approach. The outer stars, the gas clouds, the spiral arms, all are tugged and stretched by tidal forces. Just as the moon pulls on Earth's oceans to make tides, galaxies pull on each other to create enormous tides of stars and gas. These distortions can fling stars out into intergalactic space, or funnel gas toward the centers of galaxies, where it may ignite bursts of new star formation. When you think about it this way, the collision of galaxies is not destruction but creation. Gravity pulls them together, yes, but in doing so it triggers new patterns, new stars, new shapes. In the long run, this quiet, patient force ensures that the universe is never static. It is always remaking itself, slowly but profoundly. Now, if you are lying there listening, you might be tempted to think of gravity as something distant, abstract, only relevant to stars and galaxies. But remember, the very fact that you are resting on your bed right now is because of gravity. It is the same force, simply scaled down. The pull holding you to your mattress is, in a way, the same pull that is guiding entire galaxies into a cosmic embrace. It is humbling to realize that the force connecting you to Earth is also connecting the Milky Way to Andromeda. And so, as we close this part of the story, let's sit with that thought. A dull, invisible, constant force is at work everywhere, shaping the cosmos, shaping galaxies, shaping your own small life. If gravity can move galaxies across billions of years, what slow, quiet forces might be shaping your own path? Unseen, but unstoppable. When you hear the word collision, your mind probably jumps to something loud, sudden, and violent. Two cars smashing into each other on a highway, a glass slipping from a counter and shattering on the floor, even meteors hitting planets, leaving craters behind. But when galaxies collide, the picture is entirely different. It is not a crash in the sense you might expect. It is more like a slow-motion dance, unfolding across billions of years, so gradual that if you lived through it, you would never notice the movement from one year to the next. To imagine what it looks like, let's begin with a simple truth. Galaxies are mostly empty space. Stars, as bright and overwhelming as they seem when you look up, are tiny compared to the distances that separate them. If the Sun were the size of a basketball, the nearest star, Proxima Centauri, would be another basketball more than 4,000 miles away, and everything between them would be empty. That is how much space lies between stars. So when two galaxies pass through each other, the stars do not smash together like billiard balls. Instead, they pass by, weaving through one another like swarms of fireflies moving together in the night. But while the stars do not collide, the galaxies still change. Their shapes distort, stretched by the tidal pull of gravity. The great spiral arms may twist and elongate, flinging arcs of stars outward into long trails called tidal tails. These tails are some of the most beautiful features of colliding galaxies, ribbons of light stretching across space, like the remnants of fireworks frozen in time. In fact, astronomers have captured images of galaxies in mid-collision galaxies like the antennae or the whirlpool, and they look more like living art than destruction. If you try to picture it, think of two dancers spinning toward each other. As they draw near, their skirts flare out, brushing and wrapping together until they finally entwine in a single embrace. That is closer to the truth of what happens when galaxies meet. Gas clouds, however, are a different story. Unlike stars, which can slip past one another, gas clouds do collide, and when they do, they compress, heat up, and sometimes collapse under their own gravity to form new stars. That is why galactic collisions are often star factories. They trigger bursts of star formation, sometimes creating entire clusters of newborn suns in just a few million years. From the outside, it looks like the galaxies are lighting up, glowing with the energy of fresh stars being born. Now, pause for a moment and think about what that means. In the middle of what seems like chaos, creation is happening. Old structures may be stretched and reshaped, but new life in the form of stars and planets emerges from the encounter. There is something quietly reassuring in that. Change, even on a cosmic scale, does not mean only endings. It means beginnings, too. From our vantage point on Earth, if humanity somehow survived long enough to see the first stages of the collision, the changes would unfold slowly. Over millions of years, the Andromeda Galaxy would grow larger in the night sky. At first, just a brighter smudge, then a sprawling spiral rivaling the size of the Moon. Later still, its stars would streak across the sky, mingling with our own Milky Ways. To the naked eye, it would not look violent. It would look like a sky filled with more stars than anyone had ever imagined possible. This is another reminder that human words sometimes fail to capture cosmic realities. Collision suggests something fast, but in truth, it is a process. The galaxies may pass through each other more than once, swinging apart and back together like dancers in a waltz, before finally merging into one. Each passage reshapes them a little more, until at last they settle into a single larger galaxy. Let's also remember that the center of each galaxy holds a supermassive black hole. These black holes, though invisible, are like anchors at the heart of the galaxies. When the galaxies collide, their black holes, too, will begin to spiral toward one another. Over time, they may merge, releasing vast amounts of energy in gravitational waves, ripples in the fabric of space-time itself. That, however, happens later in the story. For now, it is enough to remember that even the invisible centers of galaxies are part of this slow cosmic ballet. And here's something interesting. We humans have already glimpsed what such events look like by observing other galaxies in the universe. The antennae galaxies, for instance, are two galaxies caught in the act of merging, about 45 million light-years away. Through telescopes, they appear as two distorted shapes, connected by sweeping arcs of stars. By studying them, astronomers can learn what will one day happen to the Milky Way and Andromeda. It is like watching someone else's story to predict your own future. From the perspective of science, these observations matter. But from the perspective of someone lying in bed tonight, perhaps what matters more is the thought that the universe is never static. Even the galaxies themselves are restless, moving, changing, reshaping. And if the galaxies are restless, then why should we expect our own lives to be unchanging? Perhaps we too are part of this pattern of slow, inevitable transformations that feel unsettling but give rise to new forms of beauty. So the next time you hear the phrase galaxies colliding, I hope you will not picture an explosion, but a dance. A dance so slow that no human will ever see more than the tiniest fraction of it, yet a dance so graceful that its outcome is certain. And as you drift towards sleep tonight, let me leave you with this question. If galaxies can move through each other without destruction, what else in life might pass through change without harm, transforming instead into something new? When we think about the fate of stars during the collision between the Milky Way and Andromeda, the first question that naturally comes to mind is simple. Will our sun survive? It is an oddly human question, isn't it? Out of the hundreds of billions of stars involved in this slow cosmic drama, we are really only interested in one, the ordinary star we happen to orbit. And that makes sense, because as far as we know, no other star has anything quite like Earth circling around it. The truth, however, is that the sun is unlikely to crash into anything at all. Remember how much empty space lies between stars. Even when two galaxies interweave, the odds of two stars colliding are vanishingly small. If you tried to picture it as a scaled-down model, with stars the size of grains of sand scattered across a football field, you could toss another handful of sand onto the field and almost none of the grains would hit each other. That is how much room there is in space. So in that sense, the sun is safe. But safety is not the same as certainty. While the sun may not crash into another star, its orbit inside the Milky Way will almost certainly change. Right now, the sun circles the center of the Milky Way once every 200 million years or so, tracing a steady path through one of the spiral arms. But when the Milky Way and Andromeda begin to merge, their mutual gravitational pulls will toss stars into new orbits, like a shuffle of a deck of cards. Some stars will be flung out into long looping paths. Some will be thrown entirely out of the galaxies, cast into intergalactic space as wanderers with no home. Astronomers even have a name for them: rogue stars. Imagine that for a moment. Entire suns just like ours, traveling alone in the darkness between galaxies, carrying with them any planets that might be circling. These stars would drift endlessly, never again bound to a galaxy, never again part of a grand spiral. If Earth's sun were to become such a rogue star, our night sky would vanish into blackness. The familiar river of the Milky Way would be gone. We would orbit a lonely light in an otherwise empty stretch of space. That is unlikely for the sun, but not impossible for other stars. What is much more likely is that the sun will remain bound to the merged galaxy, its orbit simply altered. It may drift farther from the center, or it may be drawn slightly inward. Either way, the view from Earth's perspective would change dramatically. As Andromeda's stars mingle with ours, the density of stars in the sky could increase, filling the heavens with light. Imagine stepping outside on a future night and seeing not just a scattering of stars, but an overwhelming canopy of brightness, thousands of times richer than what we see today. But there is a catch. By the time all of this happens, roughly 4 billion years from now, the sun itself will be approaching the end of its life. Stars like the sun have a natural lifespan, and ours is about 10 billion years. Right now, the sun is middle-aged, around 4.5 billion years old. By the time Andromeda fully collides with the Milky Way, the sun will be around 8 or 9 billion years old. That is late middle age for a star, a time when it begins to swell into a red giant, expanding until it engulfs the inner planets. Earth, if it still exists then, may not survive that phase. So, in a way, the fate of the sun during the galaxy collision is not determined by the collision itself, but by its own life cycle. The galaxy can swirl and reshape all it wants, but the sun is on a timer set by its own nuclear furnace. It will eventually exhaust its fuel, expand into a red giant, shed its outer layers, and shrink into a small white dwarf, a glowing ember of a once brilliant star. By the time the Milky Way and Andromeda have fully merged into one new galaxy, the sun will likely be long gone, reduced to that faint white cinder. This fact is quietly humbling. When people ask whether Earth will survive the galactic collision, the answer is that the collision itself is not the problem. The true problem is the passage of time, the steady ticking of the sun's life clock. Galaxies can outlast stars, but stars cannot outlast galaxies. Still, not all stars will share the sun's fate at the same time. Larger stars will already have gone supernova by then, scattering heavy elements into space. Smaller stars, the red dwarfs, far dimmer than the sun, will still be burning long after. Some of these red dwarfs can shine for trillions of years, making them the true survivors of the universe. If there are planets around them, perhaps life could find ways to endure in places we cannot even imagine. It is also worth noting that galactic collisions may influence the lives of stars indirectly. When gas clouds collide and trigger new waves of star formation, fresh generations of stars will be born. Some of these stars will form in clusters, bound together by gravity, while others will disperse into the broader galaxy. So even as old stars like the sun fade, new stars will take their place. In that sense, the collision is not just about endings. It is about renewal too. Astronomers sometimes like to think about this in terms of perspective. Our sun is special to us because we are here, circling it. But in the grand view of the cosmos, it is just one of hundreds of billions of stars, each with its own story. Some will become rogues, wandering alone. Some will form new clusters, dazzling like jewels. Some will quietly age and dim. The collision will not stop these stories. It will only shuffle them, like pages rearranged in a vast book. And maybe that is the best way to think about it tonight. Stars are characters in a story that spans billions of years. And the collision of the Milky Way and Andromeda is not the end of the story. It is simply a new chapter in which some characters fade, others rise, and the stage itself shifts into a new shape. As you close your eyes, I want to leave you with a question. If the sun itself is destined to change, fade, and pass on, what does that tell us about the impermanence of everything we see around us? And yet, if new stars are always being born, does that not also suggest that endings are never the end, but always the start of something else? If we follow the thread of this collision further, it is not just the stars that are caught in the shuffle. Entire planets, billions upon billions of them, will be affected as the Milky Way and Andromeda merge. And because planets are the cradles of potential life, the question of what happens to them carries a special weight. After all, it is not only suns that matter to us. It is the worlds that circle them, silent companions on a long orbit, each with its own story. Let us begin with a basic truth. Most planets in our galaxy will never even notice the collision. They will continue circling their stars as faithfully as Earth circles the sun. The vast empty spaces between stars mean that even as galaxies weave together, individual solar systems remain intact. It is a little like two swarms of bees passing through one another. The bees may shift and swirl, but each bee keeps flying along with its small cloud of companions. But while planets will not be smashed directly, their fates are still tied to the great gravitational shuffle. If a star is tugged into a new orbit, its planets will go with it. Imagine, for instance, a star system, much like our own, flung far from the core of the galaxy during the merger. Those planets would now orbit in a much more isolated region of space. Their skies would be darker, emptier. Night would lose its backdrop of a glowing Milky Way, replaced by thin, scattered points of light. For any life forms that might exist there, the change would be dramatic, even if their local star continued shining as before. Some planets may not be so lucky. If a star is violently tugged by gravitational forces, it is possible for its outer planets to be stripped away. They would be pulled from their orbits and cast adrift, becoming what astronomers call rogue planets, worlds without suns. These are not just science fiction curiosities. Astronomers believe that our own galaxy already holds trillions of such wanderers. Cold, dark spheres drifting silently through interstellar space, their skies black, their surfaces frozen, yet still worlds in their own right. During the galactic merger, the population of rogue planets is expected to increase. Each gravitational encounter between stars can loosen the grip that a sun holds on its outer planets, flicking them out into the cosmic void. What happens then is a kind of loneliness that is hard to imagine, a planet circling nothing, warmed only by its own faint internal heat. Some theorists even suggest that life could cling on in such places, deep beneath thick ice, where geothermal warmth still lingers. But it would be a life without day or night, without a sky, without seasons. A strange sort of survival. For inner planets, closer to their stars, the situation is more stable. Gravitational tugs are weaker compared to the strong pull of the nearby sun. So, Earth-like worlds, snug near the warmth of their stars, are unlikely to be stripped away. Their skies might fill with new stars as the galaxies merge, but their orbits would remain largely safe. Yet again, time is the larger enemy. Even if Earth were untouched by the collision, the swelling of its own sun into a red giant would end its habitability long before the galaxies fully settle. There is another fascinating outcome to consider: the birth of new planets. Remember that during collisions, clouds of gas are compressed, sparking waves of star formation. Around these newborn stars, disks of dust and gas swirl, and from those disks, new planets emerge. In other words, the galactic collision will not only fling existing worlds into chaos, it will also create new ones. Entire planetary systems, still hot and glowing, will form out of the debris. It is as if the collision clears the stage and then sets new characters upon it. We might imagine, then, that in the far future, long after Earth has vanished, new Earth-like planets could exist in the merged galaxy. Oceans could shimmer under unfamiliar suns, atmospheres could gather and swirl, and maybe, just maybe, life could arise again. Not our life, not our story, but some other life, under other stars. In this sense, the collision is not destruction, but transformation. And yet, it is worth pausing on the quieter details. Not every planet will be remarkable. Most will remain as they are now, barren, rocky, frozen, or scorched. The vast majority of worlds in the universe are not like Earth. They are lifeless stones or balls of gas. The collision will not change that. In fact, it may only emphasize it. We tend to imagine drama stars crashing, worlds flung, chaos unfolding, but the truth is often more mundane. Most planets will keep circling, unnoticed and unremarkable, as they always have. It is in this mundane truth that there is a strange kind of comfort, because the same thing is true here, for us. The Earth is, by most measures, unremarkable. A small rocky planet orbiting an average star. And yet, it is our home, our entire stage. Perhaps the future galaxies will contain billions more such small and seemingly insignificant worlds. Most will pass without notice. But somewhere, one might hold oceans, forests, or even eyes looking up at the stars, wondering the same questions we ask tonight. So, when you think about the collision of the Milky Way and Andromeda, picture not just stars swirling and gas clouds colliding, but also the quiet persistence of planets. Some will drift into darkness, some will cling to their stars, some will form anew. The details may be slow, dull, even invisible from afar, but they matter. Each planet is a possibility. Each one is a story waiting to unfold. And that brings us to the question I will leave you with tonight. If the galaxies merging means the birth of countless new worlds, then isn't it possible that somewhere, long after we are gone, another being will stand on another shore, look up at a sky filled with stars, and wonder about its place in the universe, just as you are now? When galaxies collide, one of the most overlooked but powerful consequences unfolds not among the stars themselves, but within the vast, invisible seas of gas that float between them. Stars may seem like the central players in this drama, but the truth is, stars are only one part of the stage. The real engines of transformation are the enormous clouds of hydrogen and helium drifting in galactic arms. These clouds are silent, transparent reservoirs of raw material. Most of the time, they simply float there, thin and ghostly, unnoticed. But when galaxies begin to interact, gravity and motion squeeze them, compress them, and awaken them. The result is an astonishing burst of creativity, the birth of new stars. It might help to think of it like kneading dough. You can leave flour scattered across a counter and nothing much happens, but press, fold, and push, and suddenly you have density, structure, and something new forming. Galactic collisions need gas clouds in a similar way. Where once there was just a lazy mist of hydrogen, now there are dense knots of matter that collapse under their own weight, igniting into newborn suns. Astronomers call this a starburst, and though the word may sound flashy, the actual process is slow and steady, unfolding over millions of years. During a starburst, the rate of star formation can increase by a factor of tens or even hundreds compared to normal. Imagine that in a region where a handful of stars might usually appear over eons, suddenly hundreds are born. To our eyes, if we could watch across those vast timescales, it would seem like fireworks blooming across the night. Except each spark is a sun that might shine for billions of years. And what are stars without their companions? Around many of these new stars, disks of leftover gas and dust swirl. Within these disks, the earliest building blocks of planets clump together. Tiny grains of dust collide, stick, grow, and over unimaginable spans of time, form worlds. Some of these may remain barren, some may become gas giants, some perhaps may grow oceans and atmospheres. In this way, galactic collisions are not just destructive forces, they are, in a strange sense, acts of creation. They are the universe recycling itself, turning chaos into order, dust into suns, and suns into planetary systems. It is worth remembering, though, that not all gas is evenly distributed. Some regions of the Milky Way and Andromeda are already poor in hydrogen, meaning they cannot form new stars. Astronomers believe that the eventual merged galaxy may experience a brief, spectacular starburst and then gradually run out of fuel. After that, star formation will dwindle. The skies will grow quieter, filled with aging stars but fewer young ones. It is as if the galaxy will go through a final youthful burst of energy before settling into the slow dignity of old age. One of the curious details here is that we already have examples to study. Throughout the universe, astronomers have spotted galaxies in the act of merging. Some of these collisions are so distant that the light from them left billions of years ago, but through telescopes, we can still watch the results. Take the antennae galaxies, for instance, two spirals mid-collision, their shapes distorted, their cores entwined, their arms stretched like antennae into space. In those bright knots where their gas collides, starbursts flare. These cosmic laboratories give us a preview of our own future. They show us that while collisions look chaotic, the outcome is not uniform destruction, but a pattern. Stars igniting, gas compressing, galaxies reborn in new shapes. The question, of course, is what this means for us. If Earth were somehow still around to witness it, which realistically, it will not be, what would the skies look like during this starburst? Picture this: the familiar strip of the Milky Way glowing above, but thicker, brighter, peppered with countless new pinpricks of light. The night would not be darker, but richer, more crowded. And as centuries rolled into millennia, those lights would keep multiplying. Every time you looked up, you would be gazing at the ongoing work of creation. There is also a darker side to this. For every star that is born, there are risks. Stars form in clusters, and young stars are notoriously energetic. They flare, they emit fierce winds, they blast radiation. Any newborn planets too close to this chaos might find themselves sterilized before life has a chance. In that sense, while galactic collisions open doors to new worlds, they also close many others. The balance between creation and destruction is subtle, but perhaps the most fascinating part of all this is how ordinary it is. Colliding galaxies forming new stars is not rare. It is one of the basic mechanisms by which the universe evolves. The Milky Way itself has already swallowed smaller galaxies in the past, each time sparking episodes of star formation. Our sun may even trace its origins back to one of those earlier, quieter collisions. In other words, the very existence of Earth, could be the byproduct of galactic recycling? If so, then the future starbursts of the Milky Way and Andromeda are not just abstract predictions. They are echoes of the same process that gave us life. And here is where I leave you with a thought worth carrying into sleep. When you consider the eventual merging of galaxies, do not picture only destruction and chaos. Think of the quiet, patient birth of new suns, each with the potential to host new worlds. Think of the balance between emptiness and abundance, between silence and creation. Because in the end, what is a galaxy collision but the universe reminding us that endings and beginnings are always the same thing, viewed from different sides of time? So the open question is this: if galaxies colliding can give birth to entirely new generations of stars and planets, might that mean that somewhere, someday, another Earth could rise again? Not here, not now, but in the distant future skies of a galaxy yet to be born? As we move deeper into the story of the Milky Way and Andromeda, it is impossible to ignore the black holes lurking at the centers of both galaxies. Every large galaxy has one a supermassive black hole, millions or even billions of times the mass of the Sun. These invisible titans are not like the black holes that appear in science fiction movies, swallowing everything in sight. They are mostly quiet, sitting patiently at the heart of their galaxies, holding sway over nearby stars and gas with a steady gravitational pull. Yet when galaxies collide, these giants come alive in ways that are both subtle and dramatic. Let's start with their dance. As the Milky Way and Andromeda merge, the black holes at their centers will not immediately collide. First, they will begin to orbit one another, tracing a slow, tightening spiral as the galaxies themselves twist and shift. This orbit could last millions of years, a gravitational waltz so slow that the stars around them barely notice. From our perspective, it would be imperceptible, and yet, it is a crucial step in the cosmic choreography. During this time, something remarkable happens. The black holes can influence the formation of new stars. As gas clouds fall toward the galactic centers, some of it is captured by the black hole's immense gravity. This material forms a swirling disk, heated to extraordinary temperatures, and emits intense radiation across the galaxy. Astronomers call these objects active galactic nuclei. The energy released can both trigger star formation in some regions and inhibit it in others, creating a complex interplay between creation and suppression. In other words, these black holes are not merely destructive, they are regulators, shaping the destiny of the galaxies they inhabit. Eventually, the two supermassive black holes will spiral closer and closer. When they finally merge, they will release gravitational waves, ripples in space-time that travel outward across the universe. These waves are incredibly weak by the time they reach Earth, but they carry an enormous amount of energy. In recent years, scientists have actually detected such waves from smaller black hole mergers using instruments like LIGO. So we know that when the Milky Way and Andromeda merge, the combined black hole will send out gravitational waves far larger than anything we have yet detected, silently reshaping the space around them. It is tempting to imagine these black holes as monsters lying in wait, ready to devour everything. But in reality, their influence is much more elegant, almost mundane in its persistence. They pull on stars and gas, bend light around them, and create regions of immense energy. Yet they do not roam freely, hunting planets or stars. They are bound by the same rules as the rest of the universe. Gravity is patient, predictable, and constant. One of the quieter but fascinating consequences of this black hole merger is the possible ejection of stars. As the black holes spiral inward, their gravitational interactions can sling nearby stars outward at tremendous speeds. These stars could become hypervelocity stars, racing across the galaxy, or even escaping into intergalactic space entirely. Once again, the collision reshapes the environment, quietly rearranging stars without any dramatic explosions. From a human perspective, this is almost incomprehensible. The forces at work are both immense and slow. Stars are flung across hundreds of thousands of light years. Black holes orbit each other for millions of years, and yet nothing happens quickly enough for a person to witness. It is a form of cosmic patience that stretches far beyond human lifetimes, or even the span of civilization. Yet, in its slowness, there is a rhythm, a sense of inevitability. The universe is not chaotic, it is orderly in ways we can barely grasp. Interestingly, the combined black hole will also influence the shape of the final galaxy. As it settles into the center of the newly merged Milky, as astronomers sometimes call the resulting galaxy, it will help sculpt the distribution of stars, gas, and dark matter. The spiral arms we recognize today may fade, replaced by a more elliptical structure. The future sky from a planet orbiting a star in this galaxy would be entirely different from the Milky Way we know. The familiar patterns of constellations would vanish, replaced by a dense, glowing cloud of stars in every direction. And yet, even with all this cosmic reshaping, life on small scales, planets orbiting stars far from the centers, may proceed largely unaffected. The black hole's influence is strongest near the cores, while most stars, including the Sun, are far enough away to avoid direct impact. This is another reminder that the universe operates on multiple scales at once. Enormous forces can act in one region while leaving other regions peaceful and unchanged. It is a quiet coexistence of extremes. From the perspective of a listener lying in bed tonight, this is both humbling and comforting. Even in the face of unimaginable power, there is a form of stability. Galaxies can merge, black holes can collide, stars can be flung into darkness, yet the vast majority of space remains calm. Ordinary systems, ordinary planets, and ordinary life can persist amid extraordinary change. It is as if the universe is saying, immense events do not always demand our immediate attention. Sometimes they unfold gently, over timescales far beyond our perception. And so, as you drift towards sleep, consider this. The black holes at the centers of galaxies are silent architects. They shape the cosmos in ways invisible to the naked eye, creating conditions for stars and planets, life and structure. They remind us that even in darkness and invisibility, immense power can quietly shape reality. Here is the thought to carry with you tonight. If the universe can orchestrate such precise, patient interactions between objects billions of times the mass of the Sun, what invisible forces might be quietly shaping our own lives, unseen but inexorable, guiding events in ways we do not yet understand? As the Milky Way and Andromeda continue their slow-motion convergence, one of the most fascinating consequences unfolds in the motion of their spiral arms. Galaxies, particularly spiral galaxies like ours, are not rigid structures. They are more like vast, rotating clouds of stars, gas, and dust, woven together by gravity. The arms that appear to swirl outward are patterns, waves of density where stars and gas gather, rather than solid spirals. When two galaxies approach, these waves become distorted, stretched, and sometimes flung outward entirely. Imagine two great whirlpools in a calm ocean, each spinning in its own rhythm. As they drift closer, the edges begin to tug and twist each other. Currents intertwine, eddies form, and the flow becomes complex. This is what happens when Andromeda meets the Milky Way. Stars that once moved in gentle arcs through the spiral arms are pulled into new paths. Some are drawn into long tidal tails, trailing behind the galaxies like ribbons of light. Others are caught in bridges of stars that connect the two galaxies, forming luminous pathways across otherwise empty space. The visual effect, if you could witness it, would be breathtaking. The night sky from a planet orbiting a stable star could be transformed dramatically over millions of years. One night, Andromeda might appear as a faint smudge, familiar but distant. Over time, it would swell, its stars spreading across the sky, until it dominates half the heavens. Tidal tails might stretch across vast distances, streams of light weaving through the dark void, creating patterns that no human mind could have imagined. And yet, the beauty of this process is coupled with subtle violence. Stars can be flung from their previous orbits, sent careening across the galaxy, sometimes escaping entirely. The outer regions of galaxies are particularly susceptible. Stars at the edges, less tightly bound by gravity, can be torn away and sent into intergalactic space. These are the rogue stars, wandering alone in the vast darkness, like cosmic castaways. Even in a quiet, patient universe, change carries consequences. Interestingly, the tidal forces that stretch and twist galaxies also influence star formation. Gas clouds caught in the gravitational tug-of-war can compress, collapse, and ignite into new stars. In essence, the distortion of the galaxy arms acts like a trigger, pushing gas and dust into conditions ripe for creation. Where one might expect chaos to dominate, there is instead a subtle interplay between destruction and rebirth. Some regions may see old stars scattered, while in others, whole clusters of new stars can emerge, glowing brilliantly for millions or billions of years. There is also a spatial component to consider. The stars near the centers of the galaxies are bound tightly, orbiting the dense cores with relative stability. These inner stars experience less dramatic movement than those in the outer regions, which are more vulnerable to tidal stretching. The spiral arms themselves, composed of both stars and gas, act like flexible threads, bending and reshaping but rarely breaking entirely. The structure of the galaxy is resilient, even in the face of enormous external forces. From a more human perspective, this raises a fascinating thought. Even in the midst of enormous upheaval, pockets of stability can persist. Planets orbiting stars near the center of a galaxy may see their local environment change little, even as their galactic neighborhood is transformed. The contrast between chaos and order, between tumult and calm, is a defining feature of cosmic collisions. It is not an all-or-nothing event. Much like life on Earth, change occurs unevenly, and the effects are layered across space and time. Astronomers studying other colliding galaxies give us a window into this process. The Whirlpool Galaxy, for example, is interacting with a smaller companion galaxy. Observations reveal that its spiral arms are stretched and warped, creating regions of intense star formation along the edges. Streams of stars form bridges between the galaxies, while other stars are flung into space. These images are not artistic renderings, but snapshots of real, ongoing galactic dynamics. They show us that the Milky Way Andromeda collision will be neither uniform nor instantaneous, but a long, complex process of interweaving forces. And here is a subtle, almost poetic detail. Even as tidal forces stretch stars into long streams, they create symmetry. The tidal tails, though born from gravitational violence, often mirror each other, forming arcs that radiate in opposite directions. There is a strange elegance in this symmetry, as if the universe has its own aesthetic sense, arranging matter across billions of years into patterns that are both functional and beautiful. The dance of galaxies is at once chaotic and ordered, violent and artistic. It is also worth noting the timescales involved. While we might imagine the galaxy collision as a sudden event, it is anything but. Each stage, from the initial approach to the final merging of the cores, will last millions to billions of years. Stars drift gradually, spiral arms bend slowly, gas clouds compress over eons. To a human observer, each year is imperceptible. Yet when measured in the language of cosmic time, every slight movement contributes to the larger story, shaping the final outcome. From our perspective on Earth, it is difficult to grasp the full scale of these tidal interactions. We live in short cycles of days and years, and our attention spans are tiny compared to the universe. Yet this perspective teaches us a quiet lesson. Immense processes do not require drama to be significant. The bending of spiral arms, the drifting of stars, the stretching of gas, these subtle, patient changes define the fate of entire galaxies. So as you imagine the future skies during the Milky Way Andromeda merger, picture spirals stretched into sweeping arcs, stars cast into streams, gas clouds compressed into newborn suns. Picture the quiet elegance of gravity at work, shaping the galaxies over billions of years. The night sky from a distant planet could be transformed into a glowing web of light, a testament to both change and persistence. And now, as you drift toward sleep, consider this question. If spiral arms can be stretched, stars cast adrift, and galaxies reshaped over eons without catastrophic destruction for every single star. What might that tell us about the resilience of structure and order in our own lives, even amid change we cannot control? As the Milky Way and Andromeda continue their slow-motion convergence, one of the most fascinating consequences unfolds in the motion of their spiral arms. Galaxies, particularly spiral galaxies like ours, are not rigid structures. They are more like vast, rotating clouds of stars, gas, and dust, woven together by gravity. The arms that appear to swirl outward are patterns, waves of density, where stars and gas gather, rather than solid spirals. When two galaxies approach, these waves become distorted, stretched, and sometimes flung outward entirely. Imagine two great whirlpools in a calm ocean, each spinning in its own rhythm. As they drift closer, the edges begin to tug and twist each other. Currents intertwine, eddies form, and the flow becomes complex. This is what happens when Andromeda meets the Milky Way. Stars that once moved in gentle arcs through the spiral arms are pulled into new paths. Some are drawn into long tidal tails, trailing behind the galaxies like ribbons of light. Others are caught in bridges of stars that connect the two galaxies, forming luminous pathways across otherwise empty space. The visual effect, if you could witness it, would be breathtaking. The night sky from a planet orbiting a stable star could be transformed dramatically over millions of years. One night, Andromeda might appear as a faint smudge, familiar but distant. Over time, it would swell, its stars spreading across the sky until it dominates half the heavens. Tidal tails might stretch across vast distances, streams of light weaving through the dark void, creating patterns that no human mind could have imagined. And yet, the beauty of this process is coupled with subtle violence. Stars can be flung from their previous orbits, sent careening across the galaxy, sometimes escaping entirely. The outer regions of galaxies are particularly susceptible. Stars at the edges, less tightly bound by gravity, can be torn away and sent into intergalactic space. These are the rogue stars, wandering alone in the vast darkness, like cosmic castaways. Even in a quiet, patient universe, change carries consequences. Interestingly, the tidal forces that stretch and twist galaxies also influence star formation. Gas clouds caught in the gravitational tug-of-war can compress, collapse, and ignite into new stars. In essence, the distortion of the galaxy arms acts like a trigger, pushing gas and dust into conditions ripe for creation. Where one might expect chaos to dominate, there is instead a subtle interplay between destruction and rebirth. Some regions may see old stars scattered, while in others, whole clusters of new stars can emerge, glowing brilliantly for millions or billions of years. There is also a spatial component to consider. The stars near the centers of the galaxies are bound tightly, orbiting the dense cores with relative stability. These inner stars experience less dramatic movement than those in the outer regions, which are more vulnerable to tidal stretching. The spiral arms themselves, composed of both stars and gas, act like flexible threads, bending and reshaping but rarely breaking entirely. The structure of the galaxy is resilient, even in the face of enormous external forces. From a more human perspective, this raises a fascinating thought. Even in the midst of enormous upheaval, pockets of stability can persist. Planets orbiting stars near the center of a galaxy may see their local environment change little, even as their galactic neighborhood is transformed. The contrast between chaos and order, between tumult and calm, is a defining feature of cosmic collisions. It is not an all-or-nothing event. Much like life on Earth, change occurs unevenly, and the effects are layered across space and time. Astronomers studying other colliding galaxies give us a window into this process. The Whirlpool Galaxy, for example, is interacting with a smaller companion galaxy. Observations reveal that its spiral arms are stretched and warped, creating regions of intense star formation along the edges. Streams of stars form bridges between the galaxies, while other stars are flung into space. These images are not artistic renderings but snapshots of real, ongoing galactic dynamics. They show us that the Milky Way Andromeda collision will be neither uniform nor instantaneous, but a long, complex process of interweaving forces. And here is a subtle, almost poetic detail. Even as tidal forces stretch stars into long streams, they create symmetry. The tidal tails, though born from gravitational violence, often mirror each other, forming arcs that radiate in opposite directions. There is a strange elegance in this symmetry, as if the universe has its own aesthetic sense, arranging matter across billions of years into patterns that are both functional and beautiful. The dance of galaxies is at once chaotic and ordered, violent and artistic. It is also worth noting the timescales involved. While we might imagine the galaxy collision as a sudden event, it is anything but. Each stage, from the initial approach to the final merging of the cores, will last millions to billions of years. Stars drift gradually, spiral arms bend slowly, gas clouds compress over eons. To a human observer, each year is imperceptible. Yet when measured in the language of cosmic time, every slight movement contributes to the larger story, shaping the final outcome. From our perspective on Earth, it is difficult to grasp the full scale of these tidal interactions. We live in short cycles of days and years, and our attention spans are tiny compared to the universe. Yet this perspective teaches us a quiet lesson. Immense processes do not require drama to be significant. The bending of spiral arms, the drifting of stars, the stretching of gas, these subtle, patient changes define the fate of entire galaxies. So as you imagine the future skies during the Milky Way Andromeda merger, picture spirals stretched into sweeping arcs, stars cast into streams, gas clouds compressed into newborn suns. Picture the quiet elegance of gravity at work, shaping the galaxies over billions of years. The night sky from a distant planet could be transformed into a glowing web of light, a testament to both change and persistence. And now, as you drift towards sleep, consider this question. If spiral arms can be stretched, stars cast adrift, and galaxies reshaped over eons without catastrophic destruction for every single star, what might that tell us about the resilience of structure and order in our own lives, even amid change we cannot control? By now, you might be wondering what happens to the night sky during the Milky Way and Andromeda collision. After all, much of this discussion has been about stars, gas, black holes, and dark matter. But what about the view from a planet? Even if Earth or a similar world still exists, the night sky will look entirely different over the next few billion years. It is a perspective worth imagining because it connects the grand, abstract movements of galaxies to something we can relate to, the familiar sense of stars overhead. At first, Andromeda appears as a faint smudge, just a small patch of light in the northern sky. For humans today, it is barely visible without binoculars, a distant galaxy some 2.5 million light-years away. But as it draws nearer, it slowly swells in the sky, becoming brighter and larger over millions of years. Eventually, it will dominate the heavens, stretching wider than the moon ever appears to us now. The light of its billions of stars will mingle with our own, creating a new celestial panorama. It is important to remember, though, that this is not a sudden change. Night after night, year after year, the difference is imperceptible. And yet, over cosmic timescales, the transformation is dramatic. Constellations, as we know them, will be unrecognizable. The familiar river of the Milky Way, which arches across the sky tonight, will be overlapped, twisted, and reshaped by Andromeda's stars. The night will grow richer, brighter, and more crowded with points of light. Some regions will glow intensely, where the arms of the two galaxies intersect, while other regions will be comparatively sparse, depending on the distribution of stars. One of the most fascinating features of this sky will be the tidal tails, long streams of stars pulled from each galaxy. From a planet caught in the midst of this merger, these tails would stretch across vast sections of the sky, appearing like glowing ribbons drifting in space. They are formed by the gravitational tug-of-war between the two galaxies, pulling stars outward from their previous orbits. These tidal tails are not just visually spectacular, They also serve as cosmic markers, revealing the paths and forces at work during the merger. But the changing night sky is not only a matter of aesthetics, it also signals deeper processes taking place. As gas clouds collide and compress in overlapping regions, new stars are born. These newborn stars will add new points of light to the sky, gradually filling in gaps and creating clusters of brilliant young suns. Imagine looking up and seeing areas of the sky that are unusually bright, as though countless tiny suns have just been ignited. Over millions of years, the sky becomes a record of both destruction and creation. Interestingly, this transformation would occur unevenly, depending on location. Planets closer to the center of the merged galaxy may witness the most dramatic changes, as stars in the dense core rearrange and new starbursts occur. Planets in the outer regions, where stars are more sparsely distributed, may see tidal tails sweep across the sky, but the density of stars would be less overwhelming. In every case, the familiar patterns of the night sky would be altered beyond recognition. One subtle but fascinating consequence is the potential for new types of celestial phenomena. For example, as stars move closer together in certain regions, the probability of supernovae, massive stars exploding at the end of their life cycles, could increase. Supernovae are visible across incredible distances, shining as brightly as an entire galaxy for a short period. A planet in the right location could witness multiple supernovae lighting the night sky, each one a brief, powerful testament to the ongoing life and death of stars. From the perspective of someone lying on the surface of a planet, this could be both beautiful and unsettling. The night sky would become more dynamic, more luminous, and more unpredictable, but the changes are gradual, spread over millions of years, so they would not feel catastrophic. Instead, they would create a slowly evolving cosmic landscape, a celestial story unfolding frame by frame, one night at a time. Astronomers have already studied similar phenomena in other galaxies. By observing galaxy mergers far away, they have seen tidal tails stretching across the void, starbursts igniting in overlapping gas clouds, and clusters of stars forming in places where none existed before. These distant examples offer a glimpse into our own future sky. They remind us that the universe is not static. Even the heavens we consider permanent are constantly in motion, evolving in ways too slow for a single human lifetime to fully perceive. Another interesting aspect of the changing sky is the influence of perspective. As stars move and the galaxies merge, the apparent position of objects will shift. What appears as one cluster today could become elongated or displaced over millions of years. Constellations will dissolve and reform, creating new patterns in the sky. The sky itself becomes a living map of cosmic history, a record of motion, interaction, and transformation. And yet, there is comfort in the slowness. Even as stars move and merge, planets orbit their stars with relative stability. The fundamental cycles of day and night, seasons, and planetary orbits continue largely unaffected. Life, if it exists on such planets, experiences the galaxy's grand transformations only as a slow, unfolding backdrop, like watching shadows lengthen across a vast landscape. The scale of time in galactic collisions dwarfs human perception, allowing life to persist amid enormous change. So as you imagine the night sky billions of years from now, picture it as a luminous tapestry, richer and more complex than anything we see today. Stars will have shifted, tidal tails will stretch across space, and clusters of new suns will add points of brilliance. The sky will tell the story of both galaxies, intertwined forever, a living record of cosmic dance and transformation. And as you drift towards sleep tonight, I leave you with this thought. If the night sky itself is not permanent, if it is reshaped over eons by forces we can barely imagine, what might that teach us about the impermanence and constant evolution of everything we see and cherish in our own lives? As the Milky Way and Andromeda approach one another, one of the most remarkable aspects of the collision is how energy flows through the galaxies. We often imagine collisions as violent crashes, full of noise and destruction, but in reality, the universe is quieter, more subtle. Energy moves through stars, gas, and dark matter in ways that are invisible to the naked eye, yet essential in shaping the future galaxy. Understanding this slow transfer of energy helps us appreciate the true mechanics behind the merger. Consider the stars themselves. Each star is a massive, self-contained furnace, radiating energy outward into space. When galaxies collide, these stars generally do not touch each other, but their gravitational interactions create waves and ripples in motion. Stars are tugged, nudged, and shifted in ways that gradually change their velocities. Some are sent into new orbits closer to the galactic core, others are flung outward along tidal tails. The kinetic energy of these movements, the work done by gravity over millions of years, is immense, yet it is distributed gently, quietly, almost imperceptibly. Gas clouds are even more dramatic in their response. Unlike stars, which are mostly empty space, gas clouds are diffuse but dense enough to collide. When Andromeda's clouds meet the Milky Way's, the compression generates shock waves. These shocks heat the gas, ionize it, and sometimes ignite star formation. In other words, the collision redistributes energy from motion into light, heat, and the birth of new celestial objects. The universe has a subtle way of recycling energy, turning the motion of entire galaxies into the light of newborn stars. Another fascinating phenomenon involves gravitational potential energy, the energy stored in the positions of stars and gas relative to one another. As the galaxy's mass distributions shift, this potential energy converts into motion, creating streams of stars, swirling arms, and long tidal tails. Some of this energy escapes entirely as stars are ejected into intergalactic space. In effect, the universe converts invisible potential into visible action, producing beauty without chaos, structure without explosions. Even the supermassive black holes at the centers of each galaxy play a role in energy redistribution. As they spiral toward one another, they interact with surrounding gas and stars, stirring them into motion. Matter falling into the black holes emits energy as radiation, occasionally producing jets of particles that extend thousands of light years. These outflows influence nearby gas clouds, shaping the conditions for future star formation. The energy output of these black holes is subtle on a planetary scale, but enormous when considered across the galactic landscape. It is striking to realize that the Milky Way-Andromeda collision is not primarily a destructive event. Instead, it is a massive redistribution of energy. Old stars are shifted, gas clouds ignite into new stars, black holes emit energy that influences nearby matter. Over billions of years, this energy reshaping will transform two distinct spiral galaxies into a single, more stable elliptical galaxy. Change occurs not through chaos or catastrophe, but through the quiet movement and exchange of energy across unimaginable distances. From a human perspective, this is almost poetic. We often think of change as sudden and dramatic, yet the universe demonstrates that transformation can be slow, patient, and profoundly powerful, even when imperceptible. Each star, each cloud of gas, each gravitational tug contributes to a larger narrative, a cosmic story that unfolds without haste, without noise, without urgency. It is a reminder that even the grandest events in the universe do not require spectacle to be significant. Interestingly, energy redistribution also affects the chemical makeup of the galaxies. Gas clouds collide, compress, and mix, dispersing heavier elements produced in previous generations of stars. This enrichment is essential for forming planets, atmospheres, and potentially life. Every atom of carbon, oxygen, or nitrogen in a future planetary system may owe its existence to this slow, patient process of energy and material transfer. The collision is thus not only a reshaping of structure, but also a quiet seeding of possibility. As the galaxies merge, this energy flow continues for billions of years. Even after the initial collision, stars settle into new orbits, tidal tails fade, and gas clouds slowly form new stars. The system reaches a kind of dynamic equilibrium, stable, yet always evolving. By the time Milky fully forms, the energy landscape has been thoroughly redistributed, producing a galaxy that is stable, elliptical in shape, and composed of stars both old and newly formed. One of the subtler points is that this energy transfer affects the perception of time within the galaxies. While we experience time in short-span seconds, days, years, the redistribution of energy unfolds over millions of years. To the stars and gas clouds themselves, this is a slow, almost imperceptible process. But from our perspective, it is a vast and significant transformation. The universe operates on a timescale that dwarfs human perception, yet every motion, every interaction is meaningful. And so, as you imagine the Milky Way and Andromeda colliding, picture energy flowing silently across vast distances, stars drifting gently into new orbits, gas clouds igniting into brilliant suns, and black holes quietly guiding matter with their gravity. The universe is not rushing. It is patient, measured, and precise. The drama unfolds over billions of years, yet it is no less spectacular for its quietness. As you drift towards sleep tonight, consider this. If the universe can redistribute energy so gradually and still produce breathtaking change, what might that teach us about the power of small, consistent efforts in our own lives, even when progress feels imperceptible? And the question to carry with you into sleep is this. If the vast energy of two galaxies can be exchanged so subtly yet so completely, could there be other forms of energy unseen, silent, shaping the worlds and lives around us in ways we cannot yet perceive? As the Milky Way and Andromeda finally complete their slow cosmic embrace, we reach the culmination of a story billions of years in the making. By this point, the two spiral galaxies have interwoven their stars, gas, dust, and dark matter into a single, more massive structure. Astronomers predict this newly merged galaxy, often called Milkomeda, will resemble a large elliptical galaxy, smooth, rounded, and less structured than the spirals we know today. The familiar arms of the Milky Way will vanish, replaced by a dense, glowing core surrounded by gently fading halos of stars. From a distance, the transformation is subtle but profound. Spiral patterns are replaced with an even distribution of stars. Gas clouds, largely consumed by star formation, settle into quiet regions or are expelled by the combined black hole at the core. Tidal tails and streams of stars gradually fade, leaving only faint traces of their violent past. The galaxy has grown older, calmer, and more stable. And yet, it is also different, enriched with new stars, chemically more complex, and fundamentally altered by the union of two massive systems. One of the most intriguing aspects of this final phase is the fate of the stars and planetary systems within the merged galaxy. Stars that once belonged to Andromeda now orbit the Milky Way's former center, and vice versa. Some stars are cast into the outer regions, creating a halo of displaced stars that extends far beyond the main body of the galaxy. This stellar redistribution is gentle but absolute. Orbits are altered, trajectories changed, yet most stars remain intact, their planets likely unaffected on small scales. Planets, too, continue their orbits around their stars, largely oblivious to the colossal events shaping their galactic neighborhood. Outer planets may have been flung into wider orbits, or even ejected into intergalactic space during the merger, but inner planets remain relatively stable. Life, if it exists on these planets, may endure the cosmic reshaping without noticing the larger forces at work. In this sense, the collision is both monumental and invisible, transformative yet imperceptible to those living quietly in the midst of it. The supermassive black holes at the centers of the original galaxies, having finally merged themselves, now form a single, even more massive black hole. It sits at the heart of Milkomeda, guiding the motions of nearby stars and shaping the dynamics of the core. Occasionally, it may emit radiation, or even produce energetic jets as it consumes nearby gas. But for most planets, far from the center, this is a distant whisper of influence. The core's power is immense, yet it is contained, measured, and largely invisible from afar. The sky on any surviving planets would now be unrecognizable. What was once the separate Milky Way and Andromeda now forms a dense, unified canopy of stars. The night sky would be filled with countless points of light, streams from tidal tails still faintly visible, and clusters of stars formed during the merger glowing brightly. Constellations, if they still exist, would bear no resemblance to what we know. The heavens themselves tell the story of a patient, slow-motion dance that unfolded over billions of years. And yet, despite all this change, the galaxy has reached a kind of equilibrium. Stars orbit smoothly around the dense core, gas clouds settle into quiet regions, and the rate of star formation gradually slows as fuel is consumed. Milkomeda is not a static object. It continues to evolve, but at a gentler pace, the grand turbulence of the collision giving way to measured stability. The universe has completed one of its slowest, most patient acts of transformation. One of the most humbling aspects of this final stage is realizing how little drama is actually experienced on a local scale. Galaxies are enormous, and yet stars, planets, and potential life continue quietly in their own neighborhoods. The collision, violent on a cosmic scale, is largely imperceptible to most individual worlds. It is a reminder that the universe operates across vast scales simultaneously, immense forces shaping the galaxy as a whole, while individual systems maintain a surprising degree of stability. There is also a reflective lesson in this. Even the most significant, universe-altering events unfold gradually, governed by the laws of physics and the patient hand of time. The merger of galaxies is not a sudden explosion, it is a long, deliberate process. And when it is complete, the result is a galaxy both older and richer than before, a testament to the slow, meticulous beauty of cosmic evolution. And yet, for all its scale and immensity, the story of Milkomeda does not end here. Stars will continue to age and die, gas clouds will occasionally ignite into new generations of stars, and black holes will quietly influence their surroundings. The universe never truly rests. The collision of the Milky Way and Andromeda is merely one chapter in a story that stretches back to the first moments after the Big Bang and forward into the distant, unimaginable future. So, as you lie back and drift toward sleep, consider the quiet resilience of this galaxy. Two enormous systems collided, transformed, and settled into something new. Yet life, if it exists, might persist almost unchanged. Stars continue their orbits, planets continue theirs, and the universe continues to evolve, slowly and patiently, over incomprehensible timescales. It is both awe-inspiring and comforting. Immense forces at work, yet ordinary processes quietly persisting in their midst. And here is the thought to carry into your dreams. If galaxies can collide and transform over billions of years, giving rise to new stars, new planets, and new possibilities, might our own lives be shaped by similarly patient and invisible forces, guiding growth, change, and the creation of new beginnings without our immediate perception? In the end, the Milky Way and Andromeda collision is a story of transformation, balance, and the quiet persistence of the ordinary amid the extraordinary. It is a reminder that the universe, in all its vastness, continues to create, rearrange, and evolve patiently, relentlessly, and without fanfare long after we are gone, leaving traces of its passage in the stars above. And the question I leave you with tonight is this: if the universe can create so much beauty and order through slow, silent processes, what possibilities might exist in your own life, quietly unfolding over time, waiting for their moment to shine?